We've talked about the graph of a trigonometric function before. And again, this graph is basically formed for me just like taking, like for instance here, the sine of various angles and just plotting those values as y. So I would get this graph that looks like this, but repeats forever and ever and ever, because remember, if I complete full circles, I cycle around to coterminal angles that are going to have the exact same values for the various trigonometric functions. When we start talking about the sine and cosine functions, they're periodic functions, also known as sinusoids, that can mimic certain periodic behaviors. So these periodic behaviors can often be turned into an equation involving a trigonometric function like sine or cosine. And if you're able to get a graph of a situation down to an equation, that you can start making predictions, and that's kind of the premise behind it. So when we look at a function graph here of y equals the sine of x, we had talked about before that it had a period of 2 pi, because again that goes along with coterminal angles. If I move 2 pi or a full circle from any given angle, I'm going to have the same value for the sine. So there's other parts of the graph that we're going to be spending some time with, because these things can change based on me making changes to the overall function. These graphs also have a baseline. Now, the standard baseline for a sine function is y equals 0. It's essentially a line that cuts the graph exactly in half. So for these functions here, that when I see it reaching a highest point and a lowest point, that point should be the same distance from the baseline. The amplitude is the measurement of the distance from that baseline to the highest or lowest point. So in this case here, the amplitude is 1. And then you have a starting point. And it's in quotation marks because, these graphs have no end. So if it has no end or no beginning, how can you have a starting point? Well, typically, we let a starting point, quote unquote, be, the y-axis or the y-intercept, if at all possible. So for a standard sine function, the starting point would be at 0, 0. So these are standard things that we assume to be the case for a standard sine function. But look at a cosine function. Notice that we still have the same general shape. It's still a sinusoid. However, it's just located, some things are located in different spots. But as far as certain characteristics, the period is still 2 pi. Because again, it starts repeating itself after I move a full circle away from any given angle. The baseline is still going to be at y equals 0, because that's still going to give me an amplitude of 1, for going both above and below the baseline. The only main difference between the sine function and the cosine function, as far as certain things going on, is the starting point. Since I use the y-axis as the starting point, or the y-intercept, this one's going to have a starting point at 0, 1. As I look at these graphs, I want to know these characteristics of the basic sine and cosine functions, but I also want to be aware of how it moves. Like this cosine function, I know it starts at its highest point. When I move through one period, it ends up at its highest point. Exactly halfway between the two highest points, it's at its lowest point. And at the quarter marks, halfway between the start and halfway between halfway and the end, it's when it passes through the baseline. If I keep those ideas in mind, when I start making changes and transformations of these graphs, and a lot of these are coming from similar ideas to graph transformations that we covered way back in, chapter 1 or 2? I forget which one it was specifically on top of my head at this time, but we're going to be doing similar things with graph transformations here. Because for a sine and cosine graph, if I'm given a formula of this general format, it's no longer just going to be the sine of x or the sine of or the cosine of x, or in this case the variable is going to be t. I'm going to have a number being multiplied on the outside to the sine or cosine. I'm going to have a number being multiplied to the variable. I'm going to have a number being added to the variable. I'm going to have a number being added after I've already taken the trig function value. So these four numbers are going to create changes in the overall graph of the function. When that's the case, the amplitude is going to be defined as the absolute value of a. because amplitude is a distance. Now, whether I'm going to be above or below the baseline at any given point in time, that's going to be dependent on, you know, the sign of A and some decisions we have to make as we go along with that. The period of these graphs is going to be defined by 2 pi divided by B. So B, A pretty much tells us what the amplitude is. B does not tell us directly what the period is, but it's involved in the calculation of the period. The phase shift, which is basically the same thing as a horizontal shift, is calculated by doing the opposite of C over B. So those two constants together help me describe what the phase shift is. And a vertical shift, which I have in italics because sometimes textbooks make sure to cover this and other textbooks don't. The Axford book does. It's defined as being D. So that's basically where the baseline is going to be. So if I recognize these changes, I'm able to create new graphs based off of me knowing what a sine graph usually looks like and to make the appropriate changes based off of these 4 things.